Welcome. In this video, we're going to talk about a subject which is quite important when it comes to detection of X-rays. And this is the underlying physics of all of our detectors. Well, I should say most of the modern detectors. So this subject is solid-state physics and sometimes referred to as condensed matter physics. Well, let's look at what this, this subject, where does it enter? Well, a recap of where we are in the course is that we started off with thermodynamics in order for us to understand how energy is transferred between systems. So we knew that changes in energy is going to affect changes in temperature, and changes in temperatures are going to have effects on physical dimensions of objects. And eventually we were able to quantify what energy was required to give rise to a certain change in temperature. And this came in this form of this formula. We were able to make sense qualitatively and quantitatively of energy and temperature. And moreover, we discuss different ways that energy could be transferred: conduction, convection, and also radiation. These were the different modes of energy transfer. Now, having equipped ourselves with how energy is transferred and the dynamics of energy, we were ready to understand how the energy dynamics are used in atomic physics in order to produce X-rays. And in particular, we saw that when atoms absorb energy, they will change their quantum state, and they will acquire an excited state. When an atom is in an excited state, it would emit some kind of radiation, typically photons, in order to go to a lower energy state. And that all of those dynamics could be accounted for by noting that the thermodynamic laws had to be observed. In other words, the conservation of energy had to be observed. Now, this is how nature produces X-rays, is that when an atom is in an excited state, it emits a photon in order to assume a lower energy state. Nature prefers to be in a low energy state. High energy states are not stable in nature. Having learned these lessons, we therefore exploited nature, especially in its affinity for low energy states. We exploited it in order to produce X-rays at will. That's what X-ray tubes are. They are our way of causing nature to be at an excited state, which is uncomfortable for nature. It's an unstable state. Therefore, when nature emits the extra energy which causes it to be unstable, that energy would typically be of the X-ray kind. That's what an X-ray tube is. It's nothing more than the application of the quantum mechanics, which is involved in atomic physics, together with thermodynamics. And once we have X-ray tubes, we simply introduced a patient here, or whatever anatomy we were interested in studying. We produce X-rays, and those X-rays are made to pass through a patient. And then we desire to detect them on the other side. And of course, detection depends on what you're interested in. Detection could either come this side or after optics, depending on what kind of detection you're interested in. For instance, in fluoroscopy, we typically don't want to have this kind of detection. We might introduce some kind of a photomultiplier or some kind of a fluorescent substance here before we detect, because in fluoroscopy we're interested in visible light. Okay, but the point is, we're at this point now. This is what we're interested in. We're interested in how do we detect all the X-rays that we have made to pass through a patient. And as I've mentioned, that this is a subject whose underpinning physics is of the solid state kind. Okay, Now, before we get into the details of solid-state physics, it's good for us to understand what we mean by solid-state physics. Matter is typically classified in different ways. Particularly, one of the ways we classify matter is by how it responds to different stimuli. We can classify matter by considering what are its magnetic behaviors when you expose it to magnetic fields. When matter is unresponsive to a magnetic field, which I've designated by a B field here, we call that non-magnetic. For instance, plastic. Plastic is non-magnetic because even if you apply a magnetic field, it doesn't respond to a magnetic field. Okay, another type of classification or another kind of substances we run into in the context of magnetic stimuli is ferromagnetic substances. These ones are the ones that are strongly attracted and they can be magnetized. These are the ones that can be, when you put a magnet close to them, they're strongly drawn to the magnet. So that's an example of a ferromagnetic substance. It strongly responds to external magnetic stimuli. And then you have paramagnetic ones. These ones are the ones that are weakly attracted or to both sides of a magnetic field, whether the north or the south. Typically, this is true of alloys. Some alloys, because of their magnetic properties, they may not have strong attraction to magnetic field, but there's nonetheless some amount of attraction. So they're not completely non-magnetic. And then you get the ones that are diamagnetic. These are the ones that are weakly repelled. Again, these typically are alloys. They're repelled by both sides of the magnetic field, either the North Pole or the South Pole. So that's one way we could classify matter. But this is not the only way of classifying matter. The other way we classify matter is by its electrical properties. Again, here it depends on how the object responds to a certain stimulus. In this case, our stimulus is electrical. Therefore, we can classify different materials based on how they respond to electrical stimuli. There are materials which have a very good response to electrical stimuli. In other words, when you apply electricity to both ends, you connect them to a circuit, they allow electrons to flow freely through them. These types of materials are known as conductors. Copper is a very good example. Actually, almost, and I'm being conservative here, probably 50% of all of our connection lines, I would say, are made up of copper. So copper is a very, very good conductor because it allows the flow of electrons through them. Or if you like, you could say the flow of electricity. Okay, and then there's another class or another kind of matter which responds differently when you apply electrical stimulus. And these are insulators. These ones, they actually impede the flow of electrons or the flow of electricity. A very good example of an insulator is wood. If you apply electricity through a piece of wood, there won't be any circuit. The circuit will not be closed because wood is an insulator. It does not allow the flow of electrons through it. And then the kind of matter we will be interested in, especially in the context of solid-state physics, is what we call semiconductors. Semiconductors, they have what you could call it as, they are kind of like a hybrid between an insulator and a conductor. The reason is they typically behave like an insulator, but when the conditions are suitable, they change their status and they behave like a conductor. We will talk about the understanding of how semiconductors can do this. Hence the idea of semi. because unless the conditions are right, they will not be a conductor. They will be a conductor provided that the conditions are sufficient. Okay, so this is going to be a very, very special type of matter for us. Actually, all of our digital age, our digital devices in this digital age have this kind of material somewhere in its circuit, if not most of it. Okay, and then finally we have what we call superconductors. These are very exotic and they need very, very special conditions, but for the sake of completeness, I wanted to mention them. Superconductors, these are substances or materials that provide zero, almost zero resistance to the flow of electrons or electricity. Unfortunately, although this is a very, very nice type of property in a material, unfortunately it requires very special conditions or exotic conditions which cannot be provided at a large scale. If we could make superconductors work at everyday room temperature, we would literally have zero losses in our conduction of electricity from the power station to your household. We would have zero loss. Whatever is produced would make it into your household. Whatever the source supplies would be on the output. But unfortunately, it's not a universal property, and it needs very, very special conditions. Okay, so the key takeaway point here is that solid-state physics is related to matter that responds to electrical stimulus. And moreover, it has to have a certain type of a bond, if you like. So electrically, solid-state devices are semiconductors. In other words, they have insulator and conductor properties. But then as far as state or bonds are concerned, they are solid. Of course, we have different kinds of detectors. For instance, we have detectors that use gas. Those are those ionization chamber detectors. But the ones we will be focusing on are the ones that are of the solid kind. You might think of these as your field detectors. Typically, they will be solid. So this brings us to another classification of matter, and that's related to bonds. Well, of course, liquid materials or substances, they have a certain amount of bonds, which is stronger compared to the bonds between gas particles or gas molecules. But solids always have a stronger bonds relative to gas and liquid. And the kinds of solids we are interested in are what we call crystalline. They are crystalline solids. What this means is that they have a regular pattern. They have a regular pattern of packaging. So they're not randomly oriented, but they have some regular structure. Sometimes they are cubic. They might have a cubic structure like this, where atoms live in the corners of this cube. Sometimes you might have different variants, but the point is this structure, whatever structure it is, it could be cubical, it could be dihedral, but the point is it needs to be regular. It needs to be regular. And this is true mainly for metals. This kind of requirement is true for metals. Metals are typically regular in their pattern. at the atomic level. Okay, so that's what we mean by solid state. Solid state, of course, we have to have strong bonds, and it has to have the appropriate electrical properties. Specifically, it needs to, when the conditions are right, conduct electricity, but when the conditions are unfavorable, be an insulator. Okay. Now, how do solids bond? Of course, when we discuss atomic physics, we were isolating atoms, singular atoms, which is quite difficult in everyday life and especially in application. Typically, we have a sample or we have a certain diameter of a sensor or of a detector. So we need to understand how large or samples with a large number of atoms work. How do they work? By doing atomic physics, we understood how individual atoms worked, but then how do they work when they are in a cluster or in this regular pattern, bonded together? Well, molecular physics actually helps us to understand this. There's three ways that solids can bond. One of them is ionic bonding. Simply put, here electrons are actually stripped from one atom to the other. Whatever atom which has extra electrons, those electrons will be stripped from the metal which has a lower electron affinity to the atom which has a higher electron affinity. Okay, that's one kind of bonding. The second kind is covalent bonding. Here is electrons are shared between atoms that make up a molecule, or atoms belonging to a sample of some interest. The point is, the electrons are always shared by the atoms participating in that bond. So, for instance, H2O, the electrons between the oxygen, maybe I should write that down, say H2O. We can write it this way, say that's oxygen, and maybe let's make that bigger. Oxygen, hydrogen, and hydrogen. Over here, the electrons that participate in bonding this hydrogen to this oxygen is actually shared. They don't belong simply to the oxygen nor just to the hydrogen, but they are shared between the two. The same goes for this side, where the oxygen shares an electron with this hydrogen. And in this kind of co-living or co-sharing of the electrons, a bond is maintained. I should mention that in bonding of solids or molecules in general, electrons are the participants. Electrons are the reason why we have bonds, molecular bonds. A different force is present or is responsible for bonding the nuclei. That's a strong nuclear force. You will talk about that in the second semester. We won't talk about it now. But right now, for molecular bonds, electrons are the main participants. And then finally, we have what is called metallic bond. This is a bond where electrons are not only shared by the two atoms closest to one another. For instance, here, I mentioned that the oxygen shares an electron with this hydrogen, and there's going to be a bond here. That bond will be covalent. And not only does the oxygen have a bond with this hydrogen, it also has a bond with another one. But it should be clear that there is no sharing of electrons between these hydrogens directly. That's what covalent bond means. It means just the ones that are participating in that bond. However, metallic bonding, it's quite impressive in that electrons are shared by all the atoms in the metal. In the metal. And typically this is when you have a pure metal. For instance, copper. Copper, if you have two copper molecules or two copper atoms like this, the electrons between or that participate in these bonds are actually not unique. They don't have a sense of belonging to either this atom, or that atom, but they are shared among all three. This is just an example of contrasting metallic bonding versus ionic and covalent. This idea actually is very useful in understanding how metals work. And remember, we are interested in crystalline solids, which are typically metals, in order for us to understand how sensors or detectors work. Okay, then this idea of metallic bonding brings us to a theory of, we call it free electron theory of metals. Here, electrons, as I've mentioned, don't have a sense of belonging to any one atom, but they belong to a pool of atoms. Just like those three copper atoms I showed earlier. If this guy has an electron, and that guy has an electron, and that guy has an electron, this electron does not have a sense of only belonging to this, and so also this electron over here does not have a sense of only belonging to this, and this one also. But all three electrons belong to all three copper atoms. This allows us to treat these electrons as though they were a gas that is all the time in motion. We could treat the electrons belonging to these three copper atoms as a gas that's floating around, constantly in motion, because these electrons don't have a sense of belonging to either atom, they just belong to all the atoms. This allows us then to understand how metals can conduct electricity, because you have electrons all the time in motion and available for conduction, for allowing electricity to pass through. In other words, imagine you have 2 cities or 3 cities and you have buses that are all the time moving. It's very easy to go from one city to another city to another city, because you have these electrons which are your carriers. They will carry the electrical current through, or well, they are the electrical current, if we mention properly. Okay, so the speed of these electrons depend on the temperature of our sample of copper. If our sample of copper is very warm or has a high temperature, then these electrons, since they are treated as a gas, they're going to speed up. The average kinetic energy is going to be large. But then, at very low temperature, these guys will also have zero kinetic energy. That's the idea, that's the benefit of this model. This actually explains a lot of the things we observe in nature. Certain substances improve their ability to conduct electricity as you heat them up. The warmer the metal, the easier it is for the metal to conduct electricity. This has to do with the fact that a metal has free moving electrons, and these electrons have motion depending on the temperature of the substance they are in. Okay. But before we go on, we have to consider that although these electrons are free to roam around and have no sense of belonging to anything, or to any of these atoms individually, but they belong to the sample, there are still some rules that these electrons need to be observed. Quantum mechanically, they need to observe a Pauli's exclusion principle. This is essentially the idea that no two electrons can occupy the exact same state. That is, they cannot have the exact same energy. That is why there was a limit to how much electrons we could house in each energy orbital. You might remember earlier on we mentioned that the maximum number of electrons we can house in each orbit or in each shell was given by 2n squared, where n is the energy shell number or the quantum number of that energy shell. So this number came because of Pauli's exclusion principle. And Pauli's exclusion principle in this kind of, well, I should say diagrammatically, this is a way we could represent Pauli's exclusion principle. That is, in the first energy orbit, when n is equals to 1, we only have 2 electrons allowed. And that means we have to have one up and one down. We cannot have both of them up because there will be 2 electrons in the same energy level possessing the exact same state. That is not allowed. But notice here in this second energy level, there are 2 electrons both up. This is forbidden by Pauli's exclusion principle. The proper electron configuration in this case should be first up, then down. First up, then down. Well, on this part of the subshell, this is still energy level number 2, but there's subshells. In the P shell, the way these electrons are filled in are first one up, one up, one up, and then one down, one down, one down. This is how you fill up the P shell. Okay, so again, this is the only way we can observe Pauli's exclusion principle. But notice, I just told you that there are electrons in metals that are just roaming around. How do these electrons roam around belonging to all the copper atoms, but not violating Pauli's exclusion principle? How is this possible? Well, we need to consider how atoms bond. Again, let's go back to our atomic shell. The atomic structure using shells. We said that an atom can be represented by these allowed energy orbits. And specifically, I made sure that these orbits were lines. These lines were to help us to identify that the blank region here was the unallowed or the disallowed region. In other words, electrons couldn't live here. They could only live in this line. Since in the lowest energy orbit, the N1 orbit, we could only house 2 electrons, the electrons could only live here, in this region. They could not live here. That was not allowed. But this is true for an individual atom. What if we had multiple of them? For instance, a sample of copper, a 63.55 gram copper sample, has this many copper atoms. Just 64 grams of copper has this many atoms. Now, how can these atoms live together in, for instance, like a thin sheet of copper like that? How can they live together and not violate Pauli's exclusion principle? Well, it turns out that when you bond the atoms what you are doing, essentially, you are bringing the nuclei closer to one another. As you bring the nuclei closer to one another, each nucleus has, for instance, a spin-up electron and a spin-down electron when it's by itself. And the same is true for this one. It has a spin-up and a spin-down electron. But as you bring them close together, notice that this electron is going to assume the same state as that electron. This would be a violation of Pauli's exclusion principle. So how do atoms bond? In other words, how do these guys live together in one sample without violating Pauli's exclusion principle? Actually, the proper way of understanding this is that these energy levels, although they are discrete when the atom is by itself, they begin to become bands when the atoms are brought together. What do I mean by bands? Essentially, this is what's happening. As the distance between the atoms is brought to zero, this is a 0 point, as we're bringing the atoms closer and closer to one another, the n equals 1 orbit is no longer just one discrete line, but it becomes two split lines, where electrons from the one atom can live on this line and electrons from the other can live on this line. And the same goes for the second orbit. The electrons that are in the second orbit from this atom and the ones that are in the second orbit for this atom, they actually do not violate Pauli's exclusion principle. It's that this energy begins to split into not just one single line, but into two lines in order to not violate Pauli's exclusion principle. Okay, but then what happens? So this example here I just mentioned caters just for two atoms. I just told you that in a sample of copper, 64 grams of copper, there's 10 to the 3 atoms, 10 to the 23 atoms. That's a lot of atoms. What this means is that you're going to have multiple splits here from one energy level into an energy, split into an energy band, essentially. The point is, there's going to be so many lines in here that this separation, this discreteness begins to fade away. This region becomes what we call an energy band. Okay, here's a demonstration of how this one line of energy, discrete energy levels at the atomic, when the atom is by itself. This is, I should say, maybe let me draw a line. Hopefully this will help out. That is, on this side, it's where the atom is individual. I would say it's at an atomic side or atomic level. But over here, it's when we have a molecular. In other words, when you have many atoms living together, many atoms together. Here I'd say single atom. The energy level is discrete when the atom is by itself, but as you bring many atoms together, that energy level becomes to split and becomes many bands or many lines which form eventually a band. It turns out this idea of having energy levels or discrete energy levels to becoming energy bands is at the center of our understanding of how semiconductors work. I will stop the video over here, and in the next one I will continue to show you what distinguishes conductors, insulators, and semiconductors from the idea of the band gap theory or band theory. Okay, I will see you in the next one.